based on that information, so I hope you all do the same. This angle is 10 degrees, and therefore this angle also is going to be 10 degrees. What is going to be the strike and dip of a hydraulic fracture dislocation?
10 degrees strike.
Which one?
The strike.
The strike is going to be, say again?
10 degrees.
10 degrees. This SH mean, it has to be a plane perpendicular to SH mean, because SH mean is the minimum principal stress, right? So it's just going to be 10 degrees. And what about the dip? 9 degrees. Do we all agree with this? Yes? That's the easy part of the problem, right? Now we go with the fault, okay? So for the fault, you not only need S3, but you also need S1. And as we have done before, if you remember, always, if this one is the direction of S1, and this one is the direction of S3, your faults should be somewhere over there, right? So in this case, this angle over here, beta, is going to be 45 degrees plus 40 degrees divided by 2, which is 20 degrees, right? And that's going to be equal to 65 degrees. All right. So we're getting closer to the solution. All right. So let's do that. Now I have to draw these angles so that it's an angle that goes 65 degrees from here to the angle of the fault. Okay? So let's see. This is 10 degrees. Trying to get it right with these other two directions. So this angle should be already 80 degrees. So this one the angle of one of the faults, and the other one should be somewhere over there, where this angle is 65 degrees. For this angle too is 65 degrees. All right, so now it gets a little more complicated in order to figure out the strike. But if that's 65 degrees, that means that a line here also is going to be 65 degrees. So this angle over here has to be 25 degrees, right? And if this is 25 degrees, that means that the strike is minus 10 is 15 degrees from the north towards the east. So fault strike is 15 degrees. You see, in this case, it's just easier to go with this notation towards the west. other one is going to be parallel to that one, right? And this one is 65, this should be 35 plus 10, should be 45 degrees from the north towards the east. This is particularly a little bit of a complicated one, guys. I'm not going to make your life as difficult later in the exam, okay? But I just want to show that the concept applies to this problem as well. And what's going to be the dip? The dip is going to be easy. It's an easy one. It's going to be 90 degrees, right? So these are faults are going to look more or less like this, with dip is equal to 90, perpendicular to, those are perpendicular planes, or vertical planes. Because intermediate stress is a vertical, and those lines have to contain, the planes have to contain those lines. All right, so always following this procedure, you're going to be able to calculate strike and angle for an ideal set of faults. And it's going to be always very similar to this. You just have to recognize what is the maximum principal stress, what is the minimum, and according to that, you can see what is going to be the orientation of those fault lines. Yes?
Are there more examples in your notes?
There are more examples in the homework. In the notes, I think I just have these two, or probably one more. But there are more examples that we're going to work on, and we're going to show the solution later on when we go through the homework solution. Okay? So try to work on your own on these ones, and then you'll see that as soon as you solve one or two, then later it's gonna be easier. Okay? All right. So we have talked about one application of analysis of faults, which is number one, ideal orientation of faults, which is related to the orientation of the principal stresses. So in the problems I gave you, you knew what was the orientation of principal stresses, and you can tell what is the ideal orientation of faults. But the problem could be the opposite. You could detect some faults through seismic or through some other methods, and tell, according to that, what is the orientation of principal stresses that cause those faults. And this was the example that I showed last time, and I shared with you this image over here, where we have an actual reservoir formation from the Middle East, and in which we're trying to understand what are the stresses acting on those on this reservoir. The solution was that because of the angle of those and the orientation of the anticline, which is bulking up something like this, the solution was this: that those faults, those lines that you see there, are faults which are located in this area, faults and fractures. And because of that too, we know, and we're going to get later on to the third application of this problem, is that it's much more likely that the faults oriented in this direction are more hydraulically conductive than any other faults, say, in this direction. So probably if you wanted to place a horizontal wellbore in this location, you may want to put a horizontal wellbore that goes in this direction, and not in that one. Because if you just If you had money just to put one horizontal wall in this direction, probably you will just drain the area around this area, but you will not take advantage of those fractures. If you put the horizontal wall in this direction, you will take advantage of all those fractures that can take fluid from the matrix, say somewhere around here, through the fracture, which is going to be sort of a highway, directly to the wellbore. So it's very important to know which are the fractures that are likely to be reactivated, likely to be failing, likely to have a higher component of shear to normal stress, with the location, the Mohr circle closer to shear failure, because that's going to tell us which fractures have the highest permeability. We're going to get back to this, okay? The second problem that we need to solve, and is linked to the third one, is to know what are the chances of having fracture reactivation in shear, or it will be similar fault reactivation, and also in shear, due to increased or high shear stress to normal stress. And in order to do that, we need to calculate shear stress and normal stress in a given plane. Okay? So, let me play a little bit with this toy now. Basically, what we want to do is, knowing the state of stresses, we want to calculate what is going to be the shear stress and the normal stress on this plane in order to know if this is going to move, okay? So you look, now I'm twisting this, and this is going in this direction. This is similar to a tectonic strain. And as I move it in this direction, this one is going up. In this case, with the stresses I have, I'm causing these blocks to move up. I have a normal stress here, which is going in this direction, and a shear stress, which it's applied on this face, that it goes down and here it goes up, but the final result is that this layer goes up. Do you remember what is the name of this type of faulting? So this one is what we call reverse, okay? With maximum principal stress in this direction and the minimum in here. If I were to have the opposite, so let me come back to the initial location. Say it starts here, and I have what is called an extensional regime, where the tectonic movement makes this basin to expand in this direction, or just to stay like that and to fail in shear, then we'll have the opposite. Now the block goes down, and now the minimum principal stress is in this direction, and this one goes down. And this is what is called a normal fault. This part goes down relative to the other one. Which is a footwall in this case? These guys or this one? These two are the footwall. This is the hanging wall. Hanging wall always on top of the fault. So again, this would be normal faulting. On the other direction would be reverse. And the last one, strike slip, would be a movement in which this block moves in this direction. I could have that too. And that would be caused by stresses which come in this direction, like this. So that make this block to move in this direction like that. So, and that's why it's called strike slip, right? Because it slips in the direction of the strike. And if we have normal faulting, the fracture or the fault or the block slips down in normal direction. If we have it in the other direction, it moves up the block, the hanging wall relative to the footwall. Okay, in order to determine in which direction this moves, if we know the stresses more or less, we can tell that. But our objective now is actually going to be to calculate with numbers what is the normal stress and what is the shear stress on those planes in order to understand if this one is going to move either like this or down. We can calculate that and see what is the likelihood of that of moving or not. Do you think, guys, this looks as a drilling rig or not? Looks to me like a surveillance tower to me more than a drilling tower. Anyways, I think it's a good example. All right, so this is a real toy. Next class, when we do our laboratory class, and you all have to attend, okay? I know some of you are not attending every class. You must attend next class because you have to prepare a report about that. I'm going to bring a fancy toy, okay? Much fancier than that one. Okay, so what we want to do now is we want to calculate stresses at a given orientation. All right? So, and in order to do that, we have to use the Mohr circle. And we're going to talk about the 3D Mohr circle. So we haven't seen the 3D Mohr circle yet? No? Okay. So let's go through that. Our problem is the following. We have a given location in which I have vertical stress. I have, say, minimum principal stress over here, maximum principal stress over here, and I want to calculate what is going to be the normal stress and the shear stress on an arbitrary plane. So in this plane, because of the combination of these stresses, I'm going to have a normal stress, and also I'm going to have a shear stress. By definition, the normal stress is going to be perpendicular to that plane. The shear stress is parallel to that plane. So then what we want to do is to calculate what is sigma n and what is tau. In order to solve this problem, we're going to use the 3D Mohr circle. Okay? In any Mohr circle, we plot shear stress in the y-axis and normal stress in the x-axis. Let's assume for this particular case that this is normal faulting. Okay? It's just an example, but we need that in order to draw the Mohr circle. If this is normal faulting, I can calculate sigma h mean. I can calculate sigma h max and sigma b, and those are going to be all points in the x-axis. what is the shear stress on the planes perpendicular or in the planes of the principal stresses? 0, right? By definition, principal stress planes do not have any shear stress. So this is 0. Those 3 points, similar to what we have done before, will allow me to, I'm going to draw, this is the center of this one, let's call it C1, are going to allow me to draw 3 circles. This is going to be the circle between sigma h me and sigma b. Number 2, I'm going to draw center number 2. This is going to be another circle. And in between those 2 points, I'm also going to have a third circle. So now I have 3 circles, okay? Let's understand what those 3 circles are. Let's start with the first circle, between sigma b and sigma h me. And I'm going to draw here the same cube that we had above, and where I have sigma h, I'm going to do it in terms of sigmas, because the Mohr circle should be in terms of sigmas and sigma b. Look at this point over here. This is a point in which I have a normal stress, which is sigma b, and the shear stress equal to 0, right? Which is that plane in here? Which face of the cube? The top, the front, or the side face? This point over here. The top. This is the top, right? You all see that this is the top? What about this point over here? Which side of the cube is that? Which one? Into the page. It's the front side of this cube, right? So this one is that one. This one over here is this one. And any plane that goes from this one to that one, let's say that we have a plane like this, oriented at an angle. Wait. I mix the colors. So this circle, you're gonna see it better when I upload the note. This one is in black. So this one is going to be, if this is beta 1, that plane, I'm going to find that that plane over here, it's a plane which is a point in that circle where this angle over here is 2 beta 1. And any point in that top circle, it's a plane that goes from sigma b. So it's a plane like this, from sigma b towards sigma h me. And as I go from here to there, in the circle, I go from here to over there. So if I told you, tell me what is the shear stress and normal stress on a plane which is 45 degrees from the horizontal plane into the direction of SH mean, which is going to be that point here in the Mohr circle?
2 times 45 degrees.
So 2 2 times 45 is going to be, and that's going to be that point over there, right? If I told you that beta 1 is 45 degrees. So every point in this circle is a combination, or it's a plane that goes from here to there, and that plane is going to contain the line of sigma h. Let's go to the next one, sigma b and sigma h max. So similarly to the case before, we're going to draw a cube, and here I'm going to have again sigma h mean, sigma b, sigma h max, and now this circle over here, sigma b is the maximum, is this plane over here, and now look, the green circle goes from sigma b to sigma h max, so it goes to that plane, right? And if it goes to that plane, then that means that the plane, this circle going from here to there, are going to be all the planes that go from here, from this plane, into the plane of sigma h max, which is this one, or it's the other side is the same, in which this one is beta 2. So if that one is beta 2, then that means that if I come over here, that plane is going to be that point over here, where this one is 2 times beta 2. Is that clear? So this is a plane that goes from here to there. This is a plane that goes from here to there, with now sigma h mean containing that line. And the last one, sigma b, sigma h mean, sigma h max, is going to go, this is going to be a circle that goes from sigma h max to sigma h mean, right? So now from which plane should I start measuring the angle? From always from the maximum plane, right? So it's going to be this one. And now we're going into which direction? Are we going with a plane like this, or a plane that goes like that? The first or the second one? What?
Second.
The second, right? So it goes from the plane of sigma h max to the plane of sigma h mean. It goes like a door. You see a door that goes open from here, with a hinge here, to there. So, I have lost my microphone. Okay, so this is going to be then a plane that goes, what is that? I'm just going to draw here what is easiest for me to show that plane. In this drawing, there's going to be beta 3, and beta 3 is going to be an angle that goes from here to there. And so, if I know the orientation of the angle, and I want to calculate the state of stress in any of these planes, I can just use trigonometry and tell what that is, right? So tau, for example, for this one, is going to be the length of this line times the sine of 2 beta 1. And sigma n is going to be C1 plus the cosine of this line times the cosine of 2 beta 1. The radius times the cosine of 2 beta 1. So it's just trigonometry, okay? I'm not going to write equations here because we need 3 equations in order to do that. But we're going to solve it now with an actual problem. But after you recognize this and you see what are the right angles, it's just trigonometry calculating what is tau and what is sigma n. One more thing. We know that each of these lines represents the state of stress. So each of these lines or those circles represent state of stress of any of those 3 planes. What about if we have a plane that does not coincide with any of the principal directions? Where is that state of stress going to be located? Here in the Mohr circle. Will it be located outside the Mohr circles? Probably not, right? It would be impossible to have, with this state of stress, in state of stress 0, 0. So outside, it's not very likely. What about inside? Is there any plane where we could have a normal stress which is around this value and 0 shear stress? No, right? No, because those faces with 0 shear stress, they're already taken. And those are those 3 points. They are just 3 possible solutions for not having shear stress. All of these are possible solutions, and any plane which is not any of these planes are going to be in between those 3 circles and are going to be points inside here. These points which do not coincide are planes that do not coincide with any of the principal stresses are these kind of planes over here. And those are called oblique faults because they do not coincide with any of the principal stresses. Notice that this one coincides with sigma h max, this one coincides with sigma h min, and this one with sigma v. We could have a case later on which it doesn't coincide with any of those. And in order to solve that problem, we're going to need to do quite a bit of math in order to solve that. You have a question, Ms. Saldawe?
So the example that you drew up there, that's an oblique fault?
Yes, yes. This is the general case. Because it does not, look at the plane, does not coincide with any of the direction of the principal stresses. In this case, this plane over here, it coincides with that line. Probably I could